Hey Organic, we're going to keep talking about reactions that alkenes undergo. Today we're going to be talking about the reduction of alkenes. We'll talk a little bit more about oxidation and reduction as regards to organic chemistry and try to compare that to general chemistry in a future video. But for now, just be aware that anytime we reduce an alkene, that we're essentially just adding H's to the double bond, right, to end up with a single bond. Well, in this particular case, turns out the reagent that does this is H2. So if we take just a typical type of alkene and we want to turn this thing into a good old alkane, essentially eliminating that double bond, the way that we're going to do it is we're going to pack the system filled with H2 gas. And because normally it would require huge temperatures and pressures to get this reaction to happen, what we're going to do instead is we're going to pump it filled with a little bit of H2 gas, and then we're going to use some sort of fancy-dancy catalyst. I should say that oftentimes it's palladium, sometimes it's platinum oxide. There's all kinds of different catalysts. Really what you're looking for in terms of this kind of witch's brew is H2, right? And what this is going to do is successfully add H's, right? The A and the B that adds on there are simply the H's. This is a great example of our first note card reaction that is what's called a syn addition. Keep in mind, if we talk about syn or anti-additions, right? So Br2, for instance, was an example of where we did an anti-addition. It means that we have a stereospecific reaction, right? So this note card, not only is it a good idea to label it as a syn addition, but we should also label it as stereospecific. And so what that means is that if I choose the correct starting material where there are some different, diastereomeric or enantiomeric possibilities, that type of mechanism, that syn addition, will tend to get one type of enantiomer relative to another. To show the stereospecific nature of this reaction in the mechanism, I chose a different starting material to highlight here. Turns out the mechanism for this is pretty simple. And essentially what we're going to do, just like we did before, is we're going to take this thing that is written right now in the plane of the board, and we're going to rotate it out so that we see all the wedges and dashes. And let's actually rotate the CH3s back. So this is the way that we can show the stereospecificity of this reaction. What we're going to do is we're going to show H2 as it's kind of approaching this. By the way, it truly is attached to the catalyst, but we don't care too much about that. And so we can think about this thing reacting in the kind of normal way here, where both of those hydrogens can either come in from the top or both of them are going to come in from the bottom. And you can notice this is very different than the anti-addition mechanism of Br2, where we kind of pop one of the added things on to the top, and then the other one is forced to add onto the bottom. So it turns out that a syn addition is going to pretty much take both of those, here we go, both of those wedges and dashes and move them in the same way, as opposed to what happened in anti, where one kind of goes up and then the other ends up going down. So there's our product, right? And it shows all of the different stereochemistry right there. And obviously, if this was an anti-type addition, if theoretically you're able to add H's to opposite sides, you would actually have formed the diastereomer of this. So keep track of whenever I mention syn or anti, because it always has some sort of important stereochemical consequence. What we're going to do now is, since we've kind of talked about a whole bunch of different alkene reactions that all occur through what's called a heterolytic mechanism, in other words, the door kind of swings in a direction, and then we see the carbocation, et cetera, I'm going to show you a different type of reactions that alkenes can undergo that are completely different than what we've been talking about. And the good news is, anytime we talk about a different mechanism, usually that's going to open the door to some entirely new mechanistic patterns. So what we're going to talk about here is what's called radical addition. It's something that alkenes are really good at, and it has a very different mechanistic look than stuff that we've been talking about thus far. I should, by the way, mention that anytime you see a radical mechanism, it's often termed a homolytic mechanism. And that is to be contrasted with what we've already talked about, which are heterolytic mechanisms. And the real difference has to do with the type of arrows that we draw, having to do with either two electrons moving somewhere or just one electron moving somewhere. So you'll remember from our different heterolytic mechanisms here, when we started off with some sort of alkene, we always drew, let's draw it in red because that's what our mechanistic arrows generally are. When we reacted with something, it was this double-headed arrow kind of swinging out and attacking an electrophile. Heterolytic means the two electrons that used to be shared go all the way with one carbon and kind of leave one carbon alone. What we're going to start to see with what's called homolytic mechanisms here is that our alkene, for different reasons, is instead of reacting with a double-headed arrow, is going to react with what's called a fishhook arrow, to react with some sort of radical, usually represented with R dot or something like that. It turns out that because one electron has gone to form a new bond here, the other lone electron kind of gets left behind. So what you end up with are these kind of like half-looking arrows, right? And so that's a new mechanistic pattern. Let's take a look at how it actually occurs. So here's a starting material and the beginnings of some reagents. And the first thing you're probably going to look at is, we've already talked about this. Are you kidding me? Another sort of like HBr popping onto an alkene? Well, it turns out we're going to do something different here. Below the arrow, we're going to put another species. We're going to put either one of two things, usually. We're going to put either H2O2, which is called peroxide, or we're going to put a symbol, H nu, that represents light, right? Some sort of high energy light. Anytime you see the presence of H2O2 in an organic reaction, usually that means there's some sort of radical process that's going to go on. And it turns out the final product of this thing, before when we didn't have these two present, if we had HBr, we would have seen a Markovnikov addition, right? The H would have gone with the less substituted carbon. It turns out the presence of either one of these things completely changes that, such that now what we're going to observe in our product is the bromine going to the less substituted carbon. So this on your note card should very clearly be labeled anti-Markovnikov. And so anytime you see something surprising, that's almost always going to be told to you by the mechanism. So let's see the mechanism. One of the things you'll notice I'll have to do with this mechanism is to really make some space for myself. Okay, now we have enough space to tackle this mechanism. First thing that you're going to notice is that I like to always put like the final product anytime I do a mechanism, just so that I can remember where I'm headed. And so this guy actually starts off with a very specific sequence of steps. The first step is called initiation. It turns out that initiation is a step that's required to get to what's called a propagating radical. Just about every radical mechanism that we'll talk about involves the production of what's called a propagating radical. So hold with me here and we'll see what happens. So in the case of the reaction with peroxides, we're going to start by kind of drawing an abbreviated peroxide linkage here. And it turns out that hydrogen peroxide is really good at doing homolytic bond cleavages. And so what will happen as a result of this is that very quickly I will end up with these super reactive radicals, right? Just like we've heard about, radical formation in like the body and things like that, can be pretty dangerous to have radicals around. Turns out that this oxygen has only 7 valence electrons around it, and it really wants to react with something. Turns out the thing that this thing reacts with in a second step is my HBr. And the way that it tends to react is it forms water as a driving force. So we're going to see a flow of arrows that looks a little like that. And we're going to produce some water plus our propagating radical. So this species in this reaction is the propagating radical, right? Br dot. That's the thing that's going to get the process really rocking. Next step after initiation is, believe it or not, called propagation. Propagation. And what happens here is that Br dot comes in the presence of our starting material, which I'll just draw like that. It turns out that the Br adds to the very end here because it forms the more substituted radical carbon. Just like we saw before, we could have either had the bromine attack this carbon or the other carbon. It turns out, though, that this species, because of the more carbon species being present there, tends to stabilize that lack of electron density a little bit better. Same exact case for carbocations, if you remember those. Tertiaries were always more stable and therefore more accessible than secondaries, etc., etc. It's kind of the same reason here, right? We've got this what's called inductive stabilization through bonds to kind of stabilize that that radical being there, as opposed to the Br adding to the other position and having a dot out here, right? That wouldn't be as stable, therefore it'd be a higher hill to climb, like if you remember that lecture video. And so, well, what happens at this point? Well, it turns out that we're one step away from product formation. We need to reform our propagating radical, hence the name propagating radical. Once you have a little bit of it, you keep forming more and more and more. And the way that that's going to happen is that another HBr is going to come in the presence of our material here. And we're going to reform our propagating species, and we're also going to fish our final product out of the mix. Right? So you can see that I've put the H on there now, so there's no longer a radical. This is our product. And then, of course, we form more of our propagating radical, which can then get recycled and go back to, in this process, react with another starting material, which then forms another Br dot, which then reforms another Br dot, and we kind of see this cycle and cycle and cycle, hence propagation, until you get to the point where you essentially run out of starting material, in which case you do what's called termination, which is in your book. I'm not going to talk about it here, which can happen anytime two radicals come together. Right? And so one of the things that's true of radical mechanisms, usually they're very hard to control, right? Anytime you see some chemical plant explode, it's almost always because of some sort of radical, and you can kind of see why, right? They kind of provide their own fuel. Once they get started, they're really hard to stop. Another thing that's common here is that it's really hard to control stereochemistry. So you'll see a lot of byproducts, a lot of kind of weird scrambling of chirality centers. In this particular case, we don't really care about it because what it's going to do for us is that these really useful intermediates that we talked about, these alkyl halides, having this reaction in our tool belt now is going to make our lives a lot easier because now we'll be able to make anti-Markovnikov brominated products as well as the ones that we could already form, the Markovnikov ones with just plain old HBr. So, I hope this helps, and I hope you can see most of what I wrote down here now that I'm looking at my screen. You may not be able to. One of the things that used to be true, I used to present this very early in alkene chemistry, but then it would get people thinking that it was a lot more important than it is. I would say knowing how to do these mechanistic steps are definitely not as important as knowing the heterolytic mechanisms. By far, the most common type of mechanisms that we're going to be talking about are all heterolytic, but good to know. Every once in a while, you get a question about these. Take care.